Okay, as we're passing things in and getting a graph, let's talk. So let's begin. So as we all know, we're on this journey of, we know how fast something is changing at every moment. How do we know that? How do we know how fast something is changing every moment? What is that?
Rate of change graph.
Rate of change function, right? A rate of change function. That's how we know how fast something is changing every moment. We want to take information from that, and we want to build a model for how much we have. Accumulation, right? So we want to build accumulation function. This is just an overview of that journey for the question you had on your quiz, okay? So where does it start? It starts with an exact rate of change function, which in this case was R sub b. So it's the rate of change of the remote control airplane, right, as time goes by. So in this process, what do we do next? We have the exact rate of change. We build what next? What did we do? Approximate what? Rate of change, right? Approximate rate of change. Okay? So now you're looking at two different functions, right? You're looking at the original rate function, the curve, but you're also looking at a function that's trying to be like that curve. It's pretending to be like that curve. It's approximating that curve, but doing so how? With what? Constant rates of change, right? On a rate of change graph, a constant rate, the y value will stay the same for every interval because the rate of change is constant. So that y value is staying the same for all those points on those horizontal lines, right? Those are just a set of points that they all have the same y value, right? So they all have the same rate of change. Okay? So these steps are constant rates trying to mimic the original rate function. But if we have the real actual rate function, why would we want to make this very bad approximation of it, right? So these three steps do a very bad job of approximating that rate. Why do we want to do that? So this is a huge, important question. We have to make sure we understand. Why are we taking this beautiful changing rate function that's exact and like making it so crude and not accurate anymore? Why do we do that? Everyone, we need to know the answer to this question. I know Robert knows. I know Kyle knows. Someone in the back. Where's my list? Oh, you're off the hook. I don't have my list today. But I know colors of shirts. All right, so how about light pink shirt? Why do we make this approximate rate function with constant rates?
Because we can't make a function that tells us exactly the quantity
right.
that we want.
And why does that help us?
Because it gives us like some semblance of what's going on.
Okay. How about, is it Preston, right? What do you think? Why do we have these constant rates that are inaccurately mimicking the real rate? Why do we need that? If we've got the real rate function, why do we need that? Volunteer? Yes, sir? And how does it help us do that? Why?
Because with the rate of change, we have that constant rate of change from that
Right. It's why we spent 3 weeks on constant rate of change, because we have the mathematics of constant rate of change that can get us accumulation, can get us changes, and can let us total up those changes to get amount. But if the rate is continually changing, what do? As soon as a little time goes by or a little bit of x goes by, how can we calculate how much change it is, right? It's like impossible. But with constant rates of change, we know what a change in our quantity will be the constant rate times a change in x. And then we know that the final value of an accumulation is the initial value plus the change. And so we've got that. We've got the mechanics of constant rate of change, those core principles that allow us to actually start building something like accumulation. And so that was what you sketched in your quiz. So using those constant rates, you should have built something like this. Okay? What happens to the plane I heard lots of yeahs, so I'm...
Yeah!
Lots of people did this. Okay. So, at first the rate is negative. First the rate is negative, meaning what's happening to the height? Going down. It's coming out of this window. The first thing it's going to do is going to head down, right? The rate is negative, rate of change of height. So according to that first constant rate, we can track the accumulation of height, or the de-accumulation of height, right? And then according to the second constant rate, it's going to go down even further. And then according to that third constant rate, now positive, plane's on its way back up. And it's close to, what, by 6 seconds, it's close to 50 feet again where the window is, okay? Without constant rates, we can't do this. We can't come up with some kind of approximate for the height, or the accumulation of height. Okay, so then, from there, so when we, how is our, well, anyway, so then, what is our real goal then? Our real goal is to get the actual accumulation function, the actual accumulation of height. This is, as that step function is a crude approximation of the rate, this is then a crude approximation of the real accumulation function, which exists somehow, and looks like this, okay? Looks like this. Here's the real accumulation function. So it's a start, right? This jagged is something of a start, right? The plane is heading down at first, then heads back up. So it's not great, but it's something, right? It's something, and that's made possible by the fact that we have constant rates. dy equals mdx, and y final equals I initial plus change in y. Okay, question? This is the net accumulation. This is what you were graphing. You were graphing net accumulation, and so then the height above the ground, so I might have said height, right? I might have said height, yeah. So this is net accumulation where the 50 feet is zero change, right? 50 feet is zero change. So that's why the y value starts at 0. And then their last question on the quiz was, what if this was the true height function? How would the height graph be different than this? So then it would start at 50, and all the y values would be up 50, right? All the y values of the graph that you sketched would be shifted up 50. So that whole graph would just be up starting at 50, but look the same. Okay, so this is on the second exam, this process. The order of how we do this. This is on the second exam. Everyone should get these questions right. What do we start with in this process?
Approximate rate of change.
No, we don't start with approximate rate. Exact rate of change. We know how fast something is changing. Exact rate of change. And from that, we build approximate rate of change. We need constant rates to make any progress in this process. From approximate rate of change, we have approximate accumulation, or approximate net accumulation. And then what we haven't talked about yet is then from approximate net accumulation we get exact accumulation, the black curve there. We're not there yet in talking about it, but we can still talk about the whole process. It's on the second exam. First is exact rate of change, red curve. We build approximate rate of change out of constant rates. You're all going to get this right in the exam. It's not going to be 60, 70%. From approximate rate of change, we build approximate accumulation. And then from approximate accumulation, we can move towards getting exact accumulation. And we get it. We get it, okay? Who's going to get it right in the exam? Keep your promise. Keep your promise. Okay. Please get it right. Why? So why? Because all the nuts and bolts, all the intricacies, all the math and getting into the algebra and all that stuff, it's worthless if you don't know the big picture of what we're doing. It's worthless to do calculations and write formulas and expressions if you don't know the big picture of what we're doing. That's the big picture of what we're doing. Exact rate, approximate rate, Approximate accumulation, exact accumulation. You've been warned. You've been warned. Okay, back to the rocket basketball. So we have this rocket-powered basketball. What is that for? Of course, it's heading to Pluto to help it regain its planet status. Okay? Of course. Duh, right? Duh. Okay, so what was this? What did we say this graph was? Rate of change or accumulation? This is a velocity graph. Okay? It's a rate of change function. Relates velocity of the rocket to time elapsed since launch. We saw that before, okay? This is a rate of change function. So how do we get values of velocity? How do we get values of rate of change from this function? We zoom in, we do dy over dx, right? No. It's a rate of change function. It means the dependent variable is rate of change. It's just y values, right? Y values on this graph give us rate of change. Okay? And our goal is to develop an accumulation function whose y values or dependent variable is height of the rocket, for the same independent variable of time elapsed. Okay, that's review. So just to get us... So on your graph, that's the wrong slide. This slide. Okay, so you should all have a graph like this. I want you to highlight points on the graph starting at time equals 0. Highlight points every 0.9 seconds. Every 0.9 seconds, you're highlighting points on the graph. Do your best. I know there's no grid lines. Do your best to be accurate there. Every 0.9 seconds. Okay, so when you look at your graph that I gave you on that piece of paper, your image of that should be that was made as quantities varied. It was that graph was created, that curve was created as quantities varied. And as quantities varied, correspondence points were generated. And that curve is the record of all the correspondence points. That should be your image of a graph. Not a wire sitting on a page that someone came along and put a curved wire on your page, right? That graph came about. It emerged. It was generated as time went by and correspondence points came to be. As time went by and correspondence points came to be. And those correspondence points, and you highlighted some of those, right? You highlighted some of those. So the reason I'm showing it animated is because that should be your image of it. That should be the way you think about it when you see a graph. It came about as quantities varied, right? It came about as quantities varied. Okay, so the first point you put on there was 0.9, but so 0, 0, okay, and then 0.9. And then what, 1.8, 2.7, etc. So this point right here, at x equals 2.7. What are the coordinates of that point? and the rate at 2.7, right? That's the coordinates of that point. 2.7 and v of 2.7. Telling us that at 2.7 seconds, the rate of the rocket was v of 2.7 meters per second. Estimated to be, what is that about? 1, 2, 3, 3 point something?
3.7.
Maybe I drew it in the wrong place. I'm getting about, 3.5, something like 3.5. All right, and then you had 3.6, 4.5 is this point up here. So what's happening to the speed? What's happening to the rate of change?
It's increasing.
It's increasing. We have a changing rate of change, right? We have a changing rate of change. What's v of 4.5? About like 7? Yeah, so this, down at 2.7 seconds, the speed was about 3.5 meters per second. At 4.5 seconds, the speed is about 7 meters per second. So as time goes by, the rate increases, right? That's what this rate of change graph means. Okay. Okay, so when you did this, you defined moments, right? So we've talked about moments as being small, but now we're going to allow them to be big. Okay, so we're going to call these intervals, we're going to use the symbol delta t. Delta t is going to be the width of our chosen, or it's our chosen moment width. Delta t, chosen moment width. So we're choosing our moment width here to be 0.9 seconds. Is delta t a variable or a parameter? Is delta t a variable or a parameter? Why?
Because it's a set constant.
It's a set constant in this situation. Delta t, so as we analyze the situation, delta t is not going to change. It's the width of our moment, and it's not going to change. Now, we can come back and we can make delta t 1.2. And then when we analyze it in that situation, it stays constant. So delta t can change, but in a given situation, whatever situation we're looking at, it stays constant. That's why it's a parameter. Okay? So delta t is a parameter. Okay, so now we're going to use those points that you highlighted and those rates associated with those points to sketch our approximate rate of change function. Okay, we're going to sketch the approximate rate of change function R. Use the rate at the left side of each interval to define the constant rate for that interval. So this is similar to what we've been doing. Okay, so now you have a bunch of rates that are highlighted or specified. You're going to use those rates as the constant rate. So for each interval, at the left side of the interval, use the rate at the left side to be the constant rate for that interval. So you're just drawing. You're not writing out what R is, just drawing it to get the idea of it, right? So just drawing R. Okay, so again, that's a new function. And we want to think of that as coming to be as time goes by. So now this is highlighting what you should have sketched. This is now you've drawn two functions on the same set of axes. Now we're going to focus on the second one, which we also want to think of as it emerges, it gets generated, it gets created as time goes by, and correspondence points are created, right? Every one of these steps is just a bunch of correspondence points. And what's the same about all those correspondence points on a certain step? Say this step right here. What's the same about all the correspondence points on this step right here? That's a bunch of points. Aiden, tell me. It's the same rate, right? They all have the same y value. So that's the same rate. It's the same rate. Okay? Okay, so got that? All right, so we want, as we're working on this, we want to think about we're just now we've used the exact rate to get values for those constant rates, but now we're just going to think about that R function as it is, right? Just the R function alone to help us start building accumulation of height. Okay, so we want to look at the function that you sketched, right? The function that you sketched, this approximate rate function R. Okay, and my goal now is I want to use the idea of this R function to get this number for what's the approximate height of the rocket at 5 seconds. So over here is showing the approximate accumulation function, and specifically having emerged up to and pausing at 5. So this right here shows the value that we want to compute. So this is the approximate height at 5 seconds. Okay? How are we going to do that? So how are we going to get the approximate height of the rocket at 5 seconds? Using the idea of this R function that we generated. So what are we going to do? Somebody new. How about in the white t-shirt? Yeah. Yeah, the one who's sneezing. So how am I going to get the approximate height of the rocket at 5 seconds using this function R? This this approximate rate function. Yeah, so how do we do that? So what, can you be specific?
Taking the rate of change at each interval.
Okay. Okay, so I'm just after a number now. I just want to get the actually how high. Is it 30 meters off the ground? So it looks like something like 15, close to 15. How do I get that value, whatever that is, something close to 15 meters? So I'm not interested necessarily in making a graph. Yes, sir?
Approximate accumulation.
Yeah.
So you can add each of the intervals.
Okay. What are you adding about the intervals?
So you can start at 0 and then you add dy plus the initial y, which is 0. And then you just go through each of the intervals using points of change at each interval to add on top of one another.
Okay, and let's be specific. What is it that I'm adding? What is it that I'm adding? Go ahead. Yeah.
You're adding I consider it the y initial, but it's basically it's the change in y for each segment added up.
We're going to get a change in y for each one of those constant rates. How do I get the change in y, say, for this constant rate? Oh. Yeah, sure.
Okay, you would just find for the segment of 0.9, you would multiply the change in x, which is 0.9, times your y-axis, which is your m, or your velocity.
Right. M delta x, right? So now what is our delta x? 0.9. And we have a constant rate for that whole interval. And now, so I'm showing you here, that original rate function was t of 1.3. T to the 1.3. T to the 1.3. And so what is m for that second interval? What is the value of m for that second interval? Where did we get that rate? From where? Isn't it from the left side of the... Yeah, Jacob, so what would it be?
About 0.9.
So is m equal to 0.9?
Oh, well, it'd be R of 0.9.
Which is? So I got the formula now. 0.9, which is this is delta, sorry. Did I use t's before? Sorry. This is delta t, sorry. So this delta t, this now is what? That t value right there. I should have chosen another one. Okay? And to get that rate at, we know it's according to the original rate function, it's 1.9 to the 1.3. So that gives us a little bit of accumulation, and that's for the second interval. That's how much accumulation we'll have in the second interval. Okay? So I want you to find the approximate height of the rocket at t equals 5 using this approach. This is a numerical method. We're not building a function this time. I'm not asking you to build a function. Just find how much total change we have by the time we get to t equals 5 according to these constant rates. Go. Okay, look. In the third interval, we're assuming a constant rate equal to the rate at 1.8, right? That's what you drew. So we assumed a rate equal to the rate at the left side at 1.8. Okay, so then how do we get the corresponding change for that whole interval? It's going to be that constant rate. It keeps that rate the whole time. M delta t, right? So then our delta t is 0.9. So v of 1.8 times 0.9 equals 1.8 to the 1.3 according to the original rate function. And so that gives us the little bit of change for the third interval. The little bit of change in height for the third interval. Where do we see that? We see that right here. From there to there is the little bit of change we got for the third interval. Because in the first interval there was 0 change. You see that? In the first interval, because we assumed it was 0 for the first 0.9 seconds, that's the first interval, 0 change in height. So now by the time we get to the third interval, we assume the rate of v of 1.8, which is 1.8 to the 1.3. The rate times the change in time gives us that little bit of change. That's right there. So this is the 1.8 to the 1. What is that? Anyone got that? Nice and loud.
1.93.
Thank you. 1.93 meters. So that right there is showing the 1.93 meters for the third interval, according to that constant rate of v of 1.8. Does that make sense? So how will we then approximate the total change in height at t equals 5? What will we have to do to get the total change in height t equals 5? What? We're going to have to add them all up.
0.785 plus 1.93.
But, okay, so we're going to do that for every interval. But then what's going to happen here? Did everyone notice what happens at the end?
It's not a change of 0.9.
It's not a change of 0.9 to get to 5. So let's talk about that. So what happens is, to get this total change at 5, we need all the change summed up for what we call completed intervals. By the time we've got to t equals 5 seconds, we've completed 5 intervals. But there's also this little bit more time that's gone by in what we call the current interval. But we're not going to use a full 0.9 seconds because we're not to the end of that interval yet, right? What are we going to use instead? 0.5. So to sum up the values for the completed intervals, it will look like this. These are the first 5, and these are complete. So the delta t is always 0.9. And we're going to sum that up. But then we have a little more change for the current interval. A little more change for the current interval. And what did we say about dt? We said, or dx, right? We said it changes within a moment. So this is where dt comes in. dt is the amount of change in the current interval. So what is dt in this case? The end of the completed intervals are at 4.5. And we're currently at 5. So dt is 0.5. So it's how much we've changed in the current interval. dt is a variable, right? It changes within the current moment. So to get the value of the current, in the current delta t interval, we're going to take v of 4.5 times dt, which is 0.5, not the 0.9. So the sum total of a accumulated height, so we see it over here in the accumulation graph. It's going to be the sum of completed intervals, or the accumulation from the completed intervals, plus a little more accumulation from a part of an interval, from a part interval. So when you add all that stuff together, did anyone add those all up?
14.27.
That's right. That sounds right. 14.28. So you're going to get a value for this and a value for this. When you add them all up, you should get 14.28 meters.